Here, excited to hear what this bunch of nonsense means. Um, and it actually has a very beautiful meaning behind it, and we'll dive into that. Again, remember, our goal, the reason why this is even exciting to us is because our goal is to maximize this guy, right? And again, because this log function, right? If x increases, so does log of x, right? So maximizing log will also maximize the actual function inside. So all we care about is maximizing this thing. So let's write that down. So our goal is to maximize this, okay? Now, how do we do this? To maximize this, we want to maximize this quantity too, right? Because this is a lower bound of this guy. So if we maximize this, we're in turn maximizing this to the best of our ability. Okay? So how do we maximize this function? Well, what I'll tell you is that to maximize this and to maximize this whole function, we're going to have to do two things. We're going to have to maximize this part and minimize this part, right? And that should be pretty logical, right? Because this is a positive part and this is negative, it's being subtracted. So if this also gets maximized, then we're going to be taking away from our overall thing. You can think about it as if you're like a worker, right? Or if, I don't know, like you own a business, these are your profits, right? This is your profit and this is your cost, right? So you want your total revenue to be maximized. You're going to maximize your profit and you're going to minimize your cost, right? Okay, anyways, so let's look at each term, right? What does maximizing this thing mean, right? This is, again, the log is just there. It shows up, right? The log just shows up. But what is this actual intern thing, right? What are we trying to maximize? The expected value over all Qs. So over all of our, so again, remember, the image you need to have in mind is we have our X space and our Z space, right? Okay, where we're mapping, right, each X to some distribution Q of Z given X. Okay, so each X gets mapped to a distribution Q of Z given X. So these little pools inside, right, these are all of your Q of Z given X's. So you do it for this X, and you do it for this X, and you do it for this X. Okay? Now, what is P of Z? Remember, P of Z is the overall surrounding bubble that surrounds them all. This is what we want our latent space to look like. We want our latent space to be represented by the circle. This is a terrible drawing. I apologize. There's a lot of arrows. Let me see if I can actually, never mind. Too late. Imagine, let me do it. Actually, I'll switch colors for the first time. P of Z, right, is going to be our surrounding latent space. This is what you'll see what I mean by this, but this is what we want our individual ones to conform to. And I'll explain what that means, okay? But here's the image that you have in your head. So when we take the expected value over all Qs, that means for each one of these inputs of X going to an output Z, we want to maximize the likelihood of getting X given Z. So this is, again, the reconstruction part. So basically saying over all of your encodings, which is over all of these steps going from X to Z, we want to maximize the likelihood of getting back X from Z, right? So that means that when we go back to the X space, right, we want to maximize the likelihood of seeing X. So what this term is, let's call this term A, and this term, get out of view, 1 sec. Oh my gosh, I need some better writing software eventually. Maybe when these videos make it big and YouTube starts paying me, I'll be able to afford it. Here's B. Okay, so part A, what we're doing is we're saying, okay, this is ensuring a good reconstruction. We're saying, okay, when you encode it with Z, make sure that the probability of getting X back is high. We want to maximize that. Make sense? So you turn a Z into an X, you turn an X into a Z, and you turn that Z back into an X. We want that to be good. Okay, but the issue is, what's new about that, right? Remember in the autoencoders video we talked about, that's pretty much the whole principle of an autoencoder, right? To get good reconstruction. And you measure it however you want with whatever loss function you want. But the idea is if we just had this term in our loss, we would pretty much be a simple autoencoder. This is where the beauty comes in. We are trying to minimize this term. the KL divergence between Q of z given x and P of z. Remember, Q of z given x are each individual distribution, right? And P of z is we choose it, right? P of z, we choose it usually to be normal with mean 0 and standard deviation 1. So that's very important. We are forcing these Q of z given x's to look like a distribution in the first place. Otherwise, if we didn't have these terms, this term, right, to maximize the reconstruction, wouldn't each point just map to an exact point? That would look like the autoencoder setting, right? Instead of each point mapping to this nice distribution here, it would just map to a point. It would have no reason to even look like a distribution in the first place. So this term right here, this B term, okay, allows us to have a meaningful latent space. That's the beauty. That's what you really need to understand, is that this term is what's forcing these things to even look like distributions in the first place. And not just any distribution, but it's forcing them to look as close as they can to normal distributions, to a normal distribution with standard deviation, with mean 0 and standard deviation 1. So that's our red thing, where basically, you can imagine, here's the center of the red thing, right? Mean 0. We're trying as much as we can to force each one of these Q of z given x's inside this pool and to fit them inside. So that way we meaningfully can fill up a space, right? If we didn't do that, again, one idea is if we didn't have this term here, okay, there's going to be no distributions in the first place, right? This term allows us to have a meaningful latent space, so that now that they're all packed together, jumbled in this tight latent space, we can sample from anywhere in our latent space, okay? And we can get a meaningful representation out, okay? That is very, 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 very cool, okay? This is a beautiful idea, right? And this is kind of the heart of the variational autoencoder and kind of what makes it able to generate new images. Okay, so ideally, now that we've sort of developed this autoencoder that's learning this latent space, we should be able to pick a random point from our latent space, sample it, and reconstruct new outputs, as well as the outputs, the inputs that we originally had. But now we can sort of sample maybe here and get some mix of the two that were here. It's very, very, very cool. I'm trying to think if there's anything I'm forgetting. That in the next video, we're going to talk about how we actually sample, and especially how we train when we sample, because there's a little bit of an issue there. As you can imagine, we're going to train this using gradient descent, right? So we need this loss function to be smoothly differentiable, right? So it needs to have its derivative defined at all points. The issue is this Q of z given x, right? We're randomly sampling z's in here. We're going in here, we're saying, okay, give me this z, give me this z, give me this z, right? So that's going to be an issue. We'll talk about that. Oh, what I did want to mention is that there are, basically, this whole thing is a trade-off between turning each q's of z given x into a perfect normal distribution versus having it actually mean something and reconstruct the image. So it learns the trade-off. If you want to make a more advanced model, there are advanced models that introduce a constant here, like a beta constant here. So if you increase that beta constant, right, you're emphasizing the value of this KL divergence more, right? So that changes the way that these distributions are going to look. So we can talk about those in future videos, but I think this is good for this video. Hopefully this help clear things up a little bit. In the next video, we're going to talk about the reparameterization trick, which is a trick that we're going to use for training this. But we'll get to that later. All right, bye-bye. Have a great day.